And then I already described the algorithm. And then also, so the right side is in order to calculate type lower bound function, we need to calculate subgradient, right? And the left side, in order to calculate height upper bound function, not lower bound, because we are doing minimization, right? So going back to here. So keep in mind, so this is the equation of maximization, right? So we want to find a lower bound. And then this is a minimization problem. You follow? So in this case, we need to minimize upper bound, right? So it's upper bound and it's height here, right? So you find a solution here, and then you calculate quadratic function, and then this is our problem solution x2. So that's why for maximization problem, we need to look for tight lower bound function to approximate. And for minimization problem, we need to look for tight upper bound function to minimize. Okay? And so the tight upper bound function is the same formulation as the right side for lower bound function. Only difference is h is replaced with g. Okay? So h is called a subgradient. G is a supergradient. And the supergradient must satisfy the upper bound condition, right? On the left. So can you compare the upper bound condition on the left with the lower bound condition on the right? Right? So this function must be lower bound of the true function. And this function must be upper bound of this function, right? You follow? And because this is upper bound, so this is called a supergradient. Super, right? Above. And then this is a subgradient. Sub, right? Is sub is below, right? Okay? The only difference is this is less than equal to. This is right greater than equal to. Okay? So that's why this is what I said, right? So the beauty of MM algorithm is it can be easily generalized to different kinds of optimization problem. Okay? With minor modification. And then same here, right? So you already know, right? Three steps. 3 steps that we can find h, right? You follow? And now the question here, how we can get g, right? So this is shown in this page. I'm not going to discuss because I think you can teach yourself. This one. This one. This is how we can calculate supergradient. Again, homework 11 will not include minimization. So I believe as long as you are familiar with minimization, with maximization, you should be fine to work on minimization. Okay? So this page basically tells you how to calculate the G. So now we finish, right? Submodular minimization, you should know how to implement. Okay? So the difference is replace subgradient with supergradient. Finish, right? Okay, replace subgradient with supergradient. Replace maximization with minimization. So this is maximization, right? And then this is minimization, right? And again, so we use hat to represent upper bound, tilde to represent lower bound. Okay? To differentiate. So So now we're going to combine both. And we can even handle more complex scenarios. So let me give you another, but we need to go step by step. So you'll find something very cool. So first we know if we want to maximize function, so basically, as you know, the MM framework, right? The only difference is the tight lower bound or tight upper bound function, right? As long as you know how to calculate the tight lower bound function or tight upper bound function, you can implement MM algorithm. So for this reason, we focus on different problem settings, how to calculate the tight lower bound or tight upper bound function. So this one we know, this is a ST tilde S, right? You already know the formula, right? Which is HS plus constant, right? And then max Fs S belong to 0, 1, subject 2. ST is an abbreviation of subject 2. Size, you know, some budget. Okay? So you know this is the same, right? As above. Because if you replace the objective function with a linear modular function and handle this budget constraint is easy. You can easily find the global optimum. Okay? So which means as long as your constraint is just a size limit, right? It will not make your problem more complicated, right? But max Fs 0, 1 subject to GS greater than equal B, for example. In this case, only approximate the object function is not enough because now the constraint also involves a submodular function. Right? So we need to approximate. So that's why max, this is ST subject to G lower bound function. Okay? So this is a tight lower bound function that involves some approximation on constraint. It makes sense, right? Because, I mean, if we can find a solution, then solution, this must be greater than B, right? And because this is lower bound of G, right? Then G, of course, will be above B, right? Can you follow? So if we approximate this G as lower bound function, the solution is guaranteed to be feasible. Okay? So you can easily prove if we approximate this as a lower bound function, the solution is tight and lower bound. Okay? What mean tight? So if S is ST, this will become equivalent to original function. It's called tight. So now the question here, how about max Fs S belong to 0 and 1 subject to GS greater than less than equal to B. You know, right? You know, for example, if you remember the example of the cost, the modification cost of iPhone, right? Okay? You know the iPhone cost, the cost of set of iPhone. I'll say the overall cost of a collection of iPhones is submodular function, right? Because each time you make one more iPhone, the average price will go down. So now G could be the overall cost to make 1 million iPhone, for example. Okay? So which means I want to make 1 million iPhone, the cost is below a budget. And then the objective function f is profit, right? I want to maximize profit. The profit is measured by fs. Okay? Subject to the budget, the cost, the modification cost is below our budget. Okay, I just want you to know, I mean, this has a lot of applications, much beyond abnormal pattern detection. And how to solve the problem? How to define a tight lower bound optimization problem? I mean, first, right? Maximize, right? Maximize. Of course, I mean, it's maximization. We want to maximize a tight lower bound function. Right? So this definition should be max f st s, right? But how about constraint? Should we use upper bound or use lower bound? I mean, now you know, right? You know, use submodular, we can calculate lower bound function, right? Which is f tilde. And then if we use submodular function, then we can calculate just upper bound function. Now the question here. So in this case, should we approximate gs as a lower bound function or upper bound function? Lower bound? Then let me do both. So if you say lower bound, can we raise your hand? If you say upper bound? Nobody, right? Again, I mean, because of time limit, because of time limit, I'm not going to introduce in details. I just want to let you know, because I want to make sure the solution is feasible. The solution of the approximate problem is feasible. So in order to make sure this is feasible, so which means less than equal to b, right? Then we should use upper bound. Because if upper bound less than equal to b, then the true value, of course, will be less than equal to b, right? But if you use lower bound, then it is possible you get a solution. This is not satisfied. You follow? So for this reason, this is upper bound. Okay? So it's because we want to make sure the solution we obtained is feasible. Okay? You know, this is what we want to guarantee. Same here, right? This will also make sure the solution is feasible. So now, minimize fs subject to gs greater than equal to b. How about this problem? So minimization, right? Minimization definitely should consider minimization. We want to minimize upper bound. So for this reason, we should use hat, right? Min f hat. Hat is upper bound. Tilde is lower bound. Subject to. How about this one? How about GS? Should we use lower bound or should we use upper bound? Anyone? So if we consider upper bound, right? If we consider upper bound greater than equal to b, lower bound, the true value may not be greater than equal to b, right? You follow? If we use lower bound, if lower bound greater than b, then the true value of course will be greater than b, right? So for this reason, we should use lower bound. Tilde. You see, this is the same as this one. You follow? As you can see, if you say minimization, fs s 0, 1 subject to GS less than equal to B. You can say the type upper bound optimization problem is mean F hat S ST. So this is less than equal to, right? Less than equal to upper bound, right? Sorry, this is G, right? G. Right? It's kind of unconstrained optimization problem. Unconstrained minimization, maximization are building blocks to solve more complex problems that involve submodular function in objective function in constraint in different way. Minimization, maximization, less than equal to B, greater than equal to B, right? So now, so far, all these categories of optimization problems, we assume the function f or function g are submodular, right? How about if the function is not submodular? What should we do, right? Suppose we want to maximize a function that is not submodular. How can we handle it? This one is already a paper published by same author of the algorithm. So they say if function is not submodular, then it is always possible you can represent this as a difference between two submodular. You follow? Okay? So whatever function that is not submodular, you can always approximate this, you can always refactorize the function as a difference between two submodular. So which means I will maximize f1s minus f2s. S belong to 0, 1. How to find this maximization, right? We need to maximize lower bound, right? So how to find the tight lower bound function? So maximize f1, right? Minus, right? Which means minimize f2, right? So maximize f1, which is tilde lower bound function. And then minimize f2 hat upper bound. Okay? So then this you can apply MM framework to solve the problem. It makes sense, right? Because I want to find lower bound function, right? Then lower bound function minus upper bound function becomes lower bound function, right? You follow? So this is a magic of a combination of upper bound lower bound function. In different ways, you can solve different problems. So again, I'm not expecting you to digest everything now. In one class, but I'll give you papers in the future. If you, in case, need to use these algorithms, right? Then you can go back and look at the papers. Okay? So this is the final lecture for submodular optimization. And so I will, before I give a quick review of, overall review of a whole class. So any questions so far? What you need to be familiar with is submodular maximization. Okay? So as long as you are familiar with submodular maximization, all this stuff you can teach yourself. Okay? So that's why homework 11 will be all relevant to submodular maximization. So if you don't have questions, then we can give a quick overview of the whole class. So basically, we introduced statistics, right? So statistics include 3 components. The first one, distribution, right? Binomial, Poisson, normal distribution, right? Okay? And you know, mixed binomial, mixed Poisson, mixed normal can make more complex distributions. And also, I mean, I only focused on univariate distribution. Okay? So which means that so far, I mean, the 3 distributions are all defined for single variable. But if you want to model the distribution of blood pressure and heart rate, okay, together, right, then you need to use bivariant normal distribution. But as I mentioned, right, as long as you are familiar with univariate case, you should be able to teach yourself bivariant case. Okay? Just like optimization, right? You need to learn the basic stuff, and then you can teach yourself more complex stuff. Now, after that, we introduce MLE, maximum likelihood estimation, because each distribution has a parameter you need to estimate, right? So we assume we have some training samples that we can use to maximize likelihood. Okay? The idea is likelihood is just production of training observations. The production of the probabilities of training observations. Right? The best parameter should be the parameter that can maximize the overall probabilities, right? So this is called a maximum likelihood estimation. So the reason why we say likelihood is because a probability function, if we say the variable is given, parameter is unknown, it's called likelihood function. If the parameter is known, variable x is unknown, then it's called a probability function, right? And then we introduce hypothesis testing. Actually, I would say this part should be most challenging component, right? Non-hypothesis, alternative hypothesis, and then we use this score, right? And if we do not use this score, which is more complicated case, we use LLE, log likelihood ratio, right? And this score we know is standard normal, right? And LLE, right? We need to use empirical calibration to calculate p-value. So you still remember, right? So so this is this score, and then LLR, log likelihood ratio. This is a test statistic. So basically, I have a null hypothesis of an alternative hypothesis. I want to know which one is true. In order to measure this one, we need to calculate some score that is called a test statistic. Look at the score value, we can figure out which one is true. So this test score, either can be this score, can be LLR, can be others. Okay? This score LLR are most popular ones. So now, and then distribution plus hypothesis testing, we know formulation of isolated or subset group anomaly which is max. What's the it should include isolated detection, and then subset group anomaly detection. And this one involve max LLR S right? Okay. So for this reason, we need to learn how to solve this maximization problem, right? And then we have a numerical optimization. Which is a relax. S belong to 0, 1, 2, 0, 1. Right? I mean S or X, does not matter, right? And then it include a gradient descent. Projected actually Newton's method. Right? Newton's method basically is a MM algorithm. We use a second order Taylor expression to approximate the function. It's called Newton's method. And then submodular set of discrete optimization. Include submodular maximization. And then submodular minimization. And then submodular max or mean maximization or minimization with constraints. Right? So basically, I mean, without constraint, how to solve submodular maximization, how to solve submodular minimization, and then if we have constraint, how to handle, you'll find out this is built based on these two components, right? And then non-submodular optimization. Basically, it's if your function is non-submodular, which means it is neither submodular nor submodular, then you can present this as difference between two submodular. So I will share the papers. Okay, you can look at the papers, and there's a paper, the mathematical proof. Any function can be represented as a difference between two submodular by the same authors of the MM algorithm. Okay, so basically the authors, their research only focus on submodular optimization. 90% of their papers are about submodular optimization. It's a professor from University of Washington. Okay, so this is a summary of a whole class. So I hope you can see the logic here, right? And I believe, right? I mean, the techniques that you learn way go beyond abnormal pattern detection. So I think if you can teach yourself more advanced stuff, or if you can read some papers based on what you learn in the class, you should find it very helpful for you to learn machine learning optimization, learn machine learning and data mining. Okay. So I mean, if you only apply, I mean, entry level data scientist position, you may not be asked about optimization statistics. The more high-level positions you are, more advanced data analytics position you apply for, you'll see more theoretical stuff people will ask you. Okay? Any question? So now it's 8:20. So about the course project presentation. So each team present 10 minutes in the exam week. The scheduled exam time for this class. So each team 10 minutes. So I will ask Karen to email you a Google Excel, so you can fill in your title, the title of your project. So if you do not work on project, you need to present one paper. Any paper is fine. Any paper relevant to anomaly detection will be fine. Okay? So any question about the final project?
If you work on project, like do for presentation, do you have like make slides and everything for?
If you work on a project, then your presentation will be about your project.
For presentation, you should make slides and.
Yeah, you need to make slides. Yeah. So if you do not have a project, then you should prepare slides for one existing paper. Okay? So if you don't have a question, then maybe yes.
Code submission and the slide submission on Blackboard will be same day or as the presentation?
The project, the deadline for project submission is the last day of the exam week. 8. Okay? Any question? I mean, I already mentioned, right? You either select option 1 or select option 2, right? But if you work on both, you definitely you have a higher chance to get a higher grade. So which means your efforts will be credited for sure. Okay? So for example, right? So if you only evaluate your homework, you can get a B minus, a B plus, for example. And then you work on course project, you get a B plus. Then your final grade definitely will be above B plus. At least A minus, for example. Okay? So this is to encourage you to work on homework and also work on a course project. Right? And then you have 3 options, right? I think it will not take you a lot of time to finish. Okay? Thank you. So we'll see you next in the exam week.